Got drunk off your life, and I lost myself again. You hit just like a drug. This time I won't let you in. You're playing with fire. No, I didn't on the prey, but this time I won't collapse like I did yesterday.
Okay, welcome back to this next part in this Livestream series, where we will continue with implementing the LDSO Twitch version. Last time we have left off at the full system. We are about halfway through it, so in total this file will have about 2000 lines of code. So we need to continue at this point, and hopefully, really hopefully, we can finish it in this part. We will see. Okay, so let's continue. The next method we need here is in the full system. It's a return time void, and in the full system we have a method called trace new course, which takes in a shared pointer to a frame hashing, which we call fh. And this tracing will take place once we have a new keyframe and we want to determine new feature points in the image, and those feature points will first be traced. So this is what this method is doing as far as I understand it. And for this we need a new unique lock, mutex basically, which we call lock, and this will lock our map mutex. Because the feature points in the images, they are related to 3D points, to our map. So we need to lock that. And now we need some variables. We need integers, for example, that track us or that store some statistics, how far we are in the tracing process. So we have a trace total variable, which we initialize to 0. We have a trace good, which is also 0. A trace OOB, which is 0. A trace out, which is also 0. We have a trace skip, which is also 0. And a trace bad condition, which is 0 as well, and a trace uninitialized, which is, to our surprise, 0 as well. Next we will define a calibration matrix, a MET33F, called K for the calibration, which we initialize with MET33F, and then in this namespace we choose the identity method. So we create a an identity matrix of size 3 by 3, and we now need to fill in the individual components of this matrix. So the upper left value will be initialized using the hcalib, which is an class member, a class field. And from that we take the mpch, the calib hashing, and from that we take the fxl, where fx stands for the focal length in x and l stands for the level. So we have individual levels in our image pyramid. So we take the image, we scale the image down always by half several times, and through this we can create an image pyramid, and for each level we will have a separate fx, or basically a separate camera calibration. So we need to continue with the other values. So we have the next diagonal element, basically the one in the center, and this will be hcalib, mpch, and then fyl. So along the diagonal, or in this calibration matrix, we will have the focal lengths in pixels for each level, and on the upper right hand corner of this matrix, so 0, 2, row 0 and column 2, so the third column, we will have the principal point. So hcalib, mpch, and then cxl, and similar we have the cyl in the first row or the second row, depending on how you want to count it. Okay, after we have initialized the calibration matrix, we will start a for loop and loop through the shared pointer of type frame, which we call fr, and we loop through all the frames that we have. So for every frame, we will now create or initialize the feature points. Okay, so first we take from our current frame, we get the frame hessian, which is our host frame. So we create a shared pointer of type frame hessian. Ah, hi Rahoma. Nice to have you here. How are you? We call that the host frame, which we set equal to fr, so the frame. From the frame we get the frame hessian. Doing alright. How are you doing? Well, I'm a bit sick, I have the feeling, so maybe you can hear it in my voice. Yeah. But other than that, everything's fine. Thanks. After we have extracted the host frame, we will create a host to new SE3 transformation. Yeah, thanks Rahoma. No worries, I think it's fine. So when we have a new frame, we do not only want to trace out the new feature points in the image, but we also want to store the transformation, the relative transformation. So in this case, it's the host to new transformation. And how do we get that? We take the frame hessian. From that, we take what is called the pre-world to cam SE3 matrix. And we multiply that by host and then pre-cam to world. So we always need to pay attention that we are basically in the right coordinate system, which is kind of complicated when you are working with many of those in Visual Slam generally. So when we are moving from the camera to world, we then are in the world coordinate system. So after that, we usually need to move from the world to the cam coordinate system. You will see that we will have, we'll often have the case that we are moving in between camera space and world space, basically. Okay, here we have the host to new. So we are first moving from the camera space to the world space, and then from the world space to the new camera space. So host to new, we start with the host, and after that, by a left-hand side multiplication, we'll then move to the new frame, which is the frame hessian. Okay, after that we need to construct a new matrix, met33f, which is called krki. And this is initialized to k times, so the k matrix from above, times host to new dot rotation matrix, which is a function call, and then cast to float, which is also a method. And this is multiplied by the k inverse. So let's break it down. What does it mean? Ki is basically k inverse. R is the rotation matrix, and K is again the calibration matrix. So we just pre-multiply those matrices with each other, so that we can later reuse them. This is often done in those visual slams. We are pre-calculating values that we are using later. Okay, next we need a vector 3f, so a float 3D vector, which we call kt, and this is equal to k times host to new dot translation dot cast to float again, and that's it. So we are separating the rotation in this line and the translation into different combinations of this matrix. We could also use the translation matrix, but in this case we just take the translation vector and multiply it with the calibration matrix and store this as a new vector. So the translation vector is a 3D vector, and the rotation matrix is usually a 3x3 matrix. Okay, so this is about the rotation and translation from the host to the new frame. And next we need to also handle the image brightness adjustment. And we do that by extracting the affine light parameters, which is a 2D vector. So we create a vector to f, which we call f for affine, and this will be created using the affine light class. And from that we will have a method from to vec exposure. And this method takes in the host, or basically one frame Hessian object. From that frame Hessian object we can get an AB exposure. And it will take another frame Hessian and another exposure, and will create this from to vector that tells us how do we need to expose our images. So how do we need to change the images in brightness so that we can adjust them so that they are, I think, equal in image brightness. So here we take the AB exposure from the host, and we take the AB exposure from the frame Hessian, so from our current frame. So FH AB exposure. And we pass the values to host and then FG2L and FH FG2L. And we take the result and cast the result as a float. So we call the method, and this is what we will get. So we will get a 2D vector which contains float values. So we need to cast the result as a float because we will probably get a double from that. Ah, hi Zunix, greetings. Nice to see you here. I didn't expect you here. So what brings you here, and how are you doing, Zunix? Okay, so now we have the transformation, so the geometric transformation from one frame to the other, and we will have the image brightness transformation. And now we can go ahead. Now and initialize all the feature points. So we do that by creating a for loop, where we use the auto data type. And we create an object called feat for feature, and this is iterating through FR, which is our current frame that we are looping through here. And from this frame, we take the features. So in every frame, we will have specific corners or image regions, which will be our image features. And we loop through them, and now we want to initialize those values. Better, just saw your stream, okay? So you're feeling better because you saw my stream, or what? No, just kidding. Why better? Why better, Zunix? I hope you're fine. We didn't chat in quite a while. Okay, so for every feature that we have now, we check the feed status. And one of those states can be, for example, a member of feature, which will be a class that we will implement. And in this feature class, we have a feature status. And in this, we have several states. For example, we have an imager state. And we also check for the feed IP, which I'm not sure what this IP is. It's, I think, not the inverse depth. So we will need to check that. I just looked it up. It's imager point. So IP stands for imager point. Well, I switched back to my old company since the new one was very toxic. Oh yeah, okay. Okay, I hope it's better now. Obviously, you wrote that it's better now. What was toxic about the last company? Maybe you want to tell that here, but remember, this stream is recorded and uploaded to YouTube, so maybe nothing very personal at this point. But if you want, of course, you can tell it. So after we have checked that each feature status is imager and it is an actual imager point, so this is probably a Boolean or something. Quickly check. No, it's just the data type for the imager point. Yeah, when this is true, we want to update the imager points, which means that we create a new shared pointer of type imager point, which will be our ph, so basically the point hashing, I believe. And this is initialized with the feed and then IP. So it's taking the imager point from the feature data type and initializes this shared pointer to the imager point. It's weird that this is not called point hashing, but we will see, maybe this will get clearer later. They always blamed everyone else who was not part of the meeting to the project manager why they failed the task. Yeah. Sounds very toxic, yeah. Not a nice atmosphere, it seems, to be around. From this imager point, the ph, we call the method traceOn, which will do, as it seems, all the magic of tracing the points. So I believe that this tracing will do specific initializations of the points. I also thought that it will detect the feature points in the images, but I think this is not true. So the tracing is probably only some kind of initialization of the data structures and not so much like creating the individual points on the images, like detecting them. This traceOn method takes in the frame hashing. It will also take in the KRKI, so the calibration matrix times the rotation matrix times the calibration matrix inverted. It will also take in the calibration times the translation vector. It will take in the affine light parameters from 2 vector. It will also take in the h calib and then the MP ch, which is the calip hashing. So many things that are necessary here to create the individual traces for this imager point. Next we have several checks. So we check, for example, pH, last trace status. If this is equal to imager point status, and then IPS good, then we can increment the trace good statistics. So the ones that we have created in the beginning, these statistics will now increment them given specific states of our imager point. So in case the imager point status is IPS good, we increment the trace good. Next we copy that, and we do the same with other states. So we have this pH last trace status, then we have imager point status, and then we have not IPS good, but we have IPS bad condition. In this case, as the name already suggests, we want to increment the trace bad condition. Next we have another status, which is IPS OOB, which stands, I think, for out of bounds. So in case our image features are, of course, depending on the camera movement, are moving out of the visible image area, then these will be out of bounds, and we will increment the trace OOB value. Then we have an IPS outlier, which will increment the trace out. We also have an IPS skipped status, and in this we will increment the trace skip. And lastly, let me quickly check, because the way this is written in the original code base is a bit weird. IPS skipped for skipped frames. Yes, I think this is for the skipped frames, because, for example, when we look back at the main method, and if I search for skip, yes, here at some point we will have a boolean that tells us that we want to skip a frame. And for skipped frames, let me see. Okay, at this point it does not have an influence on the full system. But maybe there's also another situation where, for example, if you have an image sequence and you have really bad images that are not, where it is not a good recommendation to track the feature points on those images, then those might be skipped, and therefore we need to track that here. Just give me a second. Okay, so after the skipped state here, we also have a state which is very important, which is the uninitialized state, which will be true for the very first situation, where we will have no initial values. And in this case, we want to increment the trace uninitialized value. And in any case, we want to increment the trace and then total value. So in the end, for every feature that we are iterating over here, we will increment this trace total variable if the feature status is imager, and we will be able to get this imager point. And in some cases we will increment the trace good, the trace bad condition, trace out of bounds, and so on and so forth. And the question now is, of course, what do these states mean? So when do they occur? And this is left for another part in this live stream, where we will be able to implement this imager point status and actually define what those are and when they are set in this point hashing or this imager point here, and then when this last trace status is being updated. So up to this point, I think quite a few things or quite a few parts of the code are still quite confusing, I would say. But once we get to actually using what we are implementing here, I think that we will many things will get a lot clearer. So at the moment, unfortunately, we need to be very patient about what is happening behind the scenes. But once we are finished with that system, we will get to it to iterating through making it functional. Okay, the next method we need to do or to implement after this trace new course method is a procedure which we add to the full system as well, which is called activate points empty, which stands for multi-threading. And this will turn imager points into real points. So this activate points method will take imager points and turn them into real points, like major points or mature points. So how is this done? We need several if statements. The condition is we take the energy functional, which is a field member of this full system. And in this energy functional, we get the endpoints variable. And we check if this endpoints, the number of points is less than the setting that we can define, which is called desired point density, but times 0.66. So we have the setting for the desired point density, and we take 66% of that. So if our number of points, in the energy functional is less than this setting, then we want to decrement the current min act dist variable. So we have this current min act dist, which is minus equals to 0.8. And please don't ask me where this magic number comes from, and this here as well. I think this can be improved, or at least be replaced with some heuristics or other like calculated values. In this current version of the LDSO, they are simply set as threshold values, like fixed numbers, magic numbers. Make the magic number as constant. Yeah, that would be a good idea. So just I think also moving this 0.66 and 0.8 just into the settings file. I don't know, Zunix, I think you're not here from the beginning and like from the first stream, but just take a look at the settings.cc file. You see how many of those settings there are, like many magic numbers, and they are, I think they are not constant, but they are at least yeah, globally accessible. Yeah, we can do that, of course, with these values as well, but to be honest, I do not want to touch the original code base. In case I do some kind of, I will introduce some kind of error. I would need to fix that later, and I want to avoid that as much as possible, and simply implement the version of the LDSO as is in the original state, and then later I could fix that. Okay, let me read. Or the linter will call you out. Yeah, okay. Note 08. Yeah, okay. Yeah, I understand what you mean. Yeah, yeah. Okay. I will create a compromise. So I will add a to-do. If I can type. Move the magic values into a constant or into constant variables. To make it more readable. I hope that's fine with you. As I said, I do not want to touch it too much at this point, but later, when we are finished, we can of course try to improve the code. And I think there will be a lot of parts in the code where improvements can be made, because it's an active research field that is moving, of course, that is evolving. Okay, let me continue. We take as a next check the energy functional and endpoints, and we check if this is less than setting desired point density times 0.8. And if this is true, then we will decrement the current min act dist by the value of 0.5. Okay, then we have an else if. We check again for the energy functional endpoints. If this is less than setting desired point density times 0.9 in this case, we will then decrement the current min act dist by 0.2. And we have another else if, which I will copy here. So the EF, oh, I forgot the arrow. EF endpoints less than setting desired point density, and this time we have the 1.0, or I will leave the, or I will, let's keep it like that. It's more readable, I think. It's not written like that in the original code base, so I'm actually changing stuff here already. But I think this is still okay. And in this case, we decrement the current min act distance by 0.1. Okay, so this is the first block. Then we will have, so maybe I can add a comment. Conditions where we have less endpoints in energy functional than the user setting desired point density contains. I don't know. Maybe it's not proper English here. Wish you a good night and happy coding. Thank you very much, Zunix. I wish you a good night as well, of course. And see you next time. Goodbye. So these are the conditions for having less points. So we have this multiplication by, well, less or equal. Because we also have this setting here. And after that we have the same where we will have conditions there where we have more endpoints in energy functional than the user setting contains. I'm not happy with this contains word, but I'm missing the proper one at this point, so let's just keep it here. Yeah, and the condition is starting with an if the EF endpoints is less than, no, if it's greater than setting desired point density times 1.5. In this case, we will increment the current min act dist with the value 0.8. We'll not have an else if here, but we will have different values for this multiplication. The first one is 1.5, then we have 1.3, then we have 1.15. Oh, and now I see it that here we have 1.0 and here we had less than, so let me delete this equal. So here we will have less and here we will have more. Okay, so then we will have an incrementing of incrementing that by 0.5, 0.2, and when we have less than the setting, that then we increment by 0.1. Okay, so these are the two cases, and after that we check. Oh, something's wrong here. After that we check. Let's copy that. We will now check the current min act dist. If this is less than 0, then we will set the current min act dist to be equal to 0. And if the current min act dist is greater than 4, then we will set it to 4. So basically we do some clamping here. Clamp the current min act dist value to be in range 0 to 4. Unfortunately, I do not know what kind of unit we have here, if this is in pixel intensities or a geometric measure. So this would be helpful to know as well. So if this is 0 pixels or this is 0 meters or whatever this is. This is something I really wish to have as many times as possible, to know those magic values, what kind of unit do they have. Okay, so after clamping we create a new variable which will be called newest frame, I suppose. which we initialize using the frames.back method. So this will probably be a frame data type here, but I will leave it to auto now. And then we create a vector of type shared pointer of type frame hessian, and we call that frame hessians. So here we will store all of the frame hessians in a vector, and to do that we need to iterate over all our frames. So we create a for loop where we create an auto data type fr, which stands for frame, and this will loop over the frames, which will be a member of this class or a field. And for every frame we now take our frame hessians vector and say dot push back. And what do we want to push on this vector? We want to push fr and then frame hessian. Okay, next we make the dist map. That is, we will have a field that is called course distance map, and from that we call make k, which will be initialized using the hcalib, and then from that we take the mpch, so the calib hessian, to make our camera calibration values, our k matrices. And we also call course distance map and then make distance map, which needs to pass the frame hessians vector and the newest frame, and then from that the frame hessian. Okay, next we create a vector which is of type shared pointer, which is of type imagerPoint, and this is called to optimize. We need to initialize this vector, so we call to optimize, and then we call reserve, and we reserve 20,000 spaces, or size of 20,000. This is because usually we will not have the possibility to set more than 20,000 features, I think, per image. Okay, and now we want to go through all active frames. So create a for loop where we create a data type auto, and this is called host. So this will be a frame, probably, or rather a frame hessian. And this host is simply iterating through all the frame hessians that we have. So the vector that we have created here, no, not here, but here, these frame hessians will be, this will be iterated over, and then in each iteration we will check if the host is equal to the newest frame, and from that the frame hessian. If this is true, then we will continue. So we'll not break this loop, but we will begin in the next iteration without continuing what is happening, what will happen here. And what will happen here? We will initialize, similar as we did above, the transformation between the frames. Oh, this is in the previous method, like this host to new, KRKI and KT. KRKI, I mean. So here we will create another SE3 variable, which is now not called host to new, but FH to new. So the frame hashing to the new frame hashing, which is initialized using the newest frame. And from that we take the frame hashing, from which we take the pre-world to cam transformation and multiply it by host and then pre-cam to world. So again, we are moving from the camera space to the world space, and then from the world space to the camera space. So we are switching, basically we are moving from one frame to the next frame. Or we're moving from the frame hashing to the new frame hashing, or to the new frame. And this will be an SE3 transformation, so it will contain rotation and translation. It will contain an SO3, a special orthogonal group, and a translation. Then we will also need to have the camera calibration as before. So we create a MET33F, which we call KRKI, which is initialized using the course distance map. And from that we take the K matrix, the calibration matrix, and we take the second one, so at index equals 1, and multiply it by FH2new dot rotation matrix, which we cast to a float. So this is the K and the R, but we are missing the KI. So the KI is, let me quickly change something here, which is the course distance map. As before, we take the K here, but this time not the second value, but the first one, so at index 0. So the course distance map, it seems, contains a vector of calibration matrices, which are ordered in like sequentially, and we are taking the first one here, but I think we are missing something. Okay, yeah, of course we're missing something, because there is not only the calibration matrix, but there's also the calibration matrix inverted, so Ki in this case. We are not calling like something like inverse or something, but we have prepared already our calibration matrices inverted. We have inverted them as a prior operation, it seems. Okay, so we have the Ki, we have our rotation, our R, and we have the usual K. And what this is doing, if we take a point in an image and multiply it with the inverted calibration matrix, we could say we are projecting that 2D point into 3D space, so into camera space. Then we are rotating it into our like new camera. So we have this rotation matrix from our frame hash into the new camera. And then we are using the K matrix to project it back onto the image space, which will help us to transform points from one image to the other. So it's similar with the SE3 transformation here, but this one is responsible for the extrinsic motion, like the actual camera motion, and this MET33F KRKI is responsible for transforming the points. So it includes the intrinsic parameters, the camera calibration. Okay, similar as before, we also need to have a VEC3F, which is called KT, which is a combination of our calibration matrix times the translation vector. So we get to, or we call our cause distance map. From that we call the K matrix for the second frame. And we multiply that by FH2 new dot translation, and then we cast that as a float, and this is it. Next we will loop through all of our features in one frame, specifically in the host frame. So create a for loop of type size t, I equals 0, and then I is less than, count is in this case host, and then frame, and then features dot size. And we increment I. So I contains the current feature in our host frame. It will not contain the feature, but it will contain the index where we can look up the actual feature in this features object here. So let's do that, because we will need it later. We will create a new shared pointer of type feature, and we'll call it the reference to a feed, and we'll initialize it using the host and then the frame and then the features at the index I, like that. With that, now that we have the feature, the current feature, we can check the status of this feature. So we check if the feed status, if this is equal to feature, which is a data type, from that we take the feature status, and from that we take the imager status. And we check that to be true, and we also want to have the feed and then IP, the imager point. Okay, with that we can now store our feature, our imager points, and check if we can activate them. Because remember that this method that we are currently implementing is called activate points multithreading. So we will store that, the values, as shared pointers. First type is feature. Feature. Again, a reference to feed, which is equal to host, frame, and then features at index I, which, to be honest, I'm not sure why this is redefined at this point. This is really weird because we have the same line here. So I'm a bit confused why this is redefined here. It should actually throw an error due to the redefinition. But maybe given that this is a shared pointer, it will not throw an error. I do not really like that. So let me add a to-do for at a later point. Why is, or check if the redefinition in the if block is really necessary. Okay, but let's continue. We also need to have a shared pointer of type imagerPoint. I think GCC default is to just give a warning when a variable shadows another. Okay, yeah, this could be. There are actually a lot of warnings when the code is compiled. So this might be one of them. Okay, so we have this imagerPoint or ph point hashing maybe, which will be initialized using host and then frame and then features. And then imagerPoint from that. And we also initialize IDX, so ph IDX in imagerPoints, which is equal to I. So this is the iterator variable, so the index that we are using to loop over all the features. Okay, next we want to delete points that have never, not newer, but never been traced successfully, or that are outlier on the last trace. Okay, so we basically want to clean up here. So we need to check if not standard is finite, ph idepth max, or ph last trace status is equal to IPS and then outlier. So if we do not have a finite inverse depth max value, or we do have an outlier, so this is what is written in this comment basically, this has not been traced successfully, or that our outlier, that are maybe an outlier on the last trace. And then we want to update the feed and then status to be feature and then feature status and then outlier. We also want to release the imager feature, release imager. And then we want to skip the rest and continue with the loop. What is the rest? We create a Boolean variable called canActivate. And this will now have several conditions that need to be true. And the first one being the imagerPoint, the ph, and then last trace status. If this is equal to IPS, good. or pH last trace status. This is equal to IPS skipped. We know that from before. There are several other states. So the trace status can also be IPS bad condition and IPS OOB. So this is the first part. These are these conditions are combined using the OR keyword, and we have several others that are combined using the AND operator. And this is, for example, pH last trace pixel interval less than 8, and two more. The first one, or the second one here, is pH quality is greater than setting min trace quality. And we also have a last one, and pH and then eye depth max plus pH eye depth min. If this is greater than 0, then this combination is set to either true or false, depending on what is going on here. And now we can check. Now we can check if we can activate. So if first we cannot activate, so if not can activate, then we will do the following. We will say if point will be out afterwards, delete it instead. If point will be out afterwards, delete it instead. Out of what? Out of bounds, maybe? Not a very helpful comment. But yeah. If pH feature and then host.log, and then from this I think we get a frame hashing. No, we get a frame, sorry. So from the frame we can get a frame hashing, and from that we can get a variable called flagged for marginalization. So we check if this current frame hashing is flagged for marginalization, or pH and then last trace status is equal to IPS OOB. So this is the out of bounds. So probably this means if point will be out of bounds afterwards, delete it instead. Which would make more sense to me here. Okay, so our last trace status is IPS OOB. Then what will we do? We will update the feature status. So feed status is equal to feature status outlier. So this will be marked as an outlier, and we will call feed release imager. And after this if statement, we'll continue. we are still in the loop where we loop through all the features in the host frame. But now we know that we can activate. So what we will do now is we see if we need to activate point due to distance map. So we create a new vec3f called PTP, and this is equal to KRKI, so our camera calibration rotation matrix and camera calibration inverted, times vec3 f of feed and then UV at index 0 and feed UV at index 1, comma 1. So what this is, in my view, is we have this feature in the image, and this feature has a position in the image space, which is denoted by a UV variable, and the 0th element is the x coordinate, and the second, or the coordinate at index 1, is y, and then we have this third coordinate, which is the homogeneous coordinate. So this is basically w. It's often called w. So we create this homogeneous 2D vector. So we have a 2D vector plus one dimension, so we get to a 3D vector. And the nice thing about this is we can, using homogeneous coordinates, we can combine rotation and translation in one matrix, but still, as far as it seems to me, we are still separating rotation and translation here into individual steps. And I'm not sure why this is, but it will become apparent in a minute, because here we are taking this homogeneous vector and we are adding another vector to it, which we calculate using KT, so our camera calibration times the translation vector, and we multiply that by 0.5 f times the pH, so basically our imager point, and from that the eye depth max plus pH eye depth min value. So we have our translation vector, which is transformed into image or into camera space. Now let me quickly check. So we have our translation vector, frame hash into new, which is in what space? This is in camera space. Okay, so this is in camera space, and with the calibration matrix we are moving into image space. Then we are in image space. Okay, and in image space we are scaling the translation vector in image space using 0.5 times times the range of the inverse depth. Okay, I think there was some concept of projecting the, like if you have a feature point in an image, it will have an associated depth, and will also have an associated maximum and minimum depth. And it is possible to project this kind of range, this depth range, into other images and see in the images how far, or how far is the range of my depth, and this is probably utilized here. But it is a bit complicated to get the head around that. So this would be nice to visualize at some point, probably. Okay, now we have this P2P, which is basically our transformed point. PTP probably stands point to point, for point to point, so it's it is the first point in the previous image transformed onto our current or the new image. And now we want to, the problem is that we have, or not the problem, but the fact is that we will have this one as a homogeneous 2D vector. So we need to create or like undo the homogenization and convert it back into a Euclidean point. So we extract the individual coordinates, so our x and y coordinate, or as it is called here, u. So int u is equal to ptp at index 0 divided by ptp at index 2 plus 0.5 f, and we have the v ptp at index 1 plus 0.5. So this division of the x and y variable divided by the w variable, the homogeneous coordinate, will yield like the actual point in image space. I think this can also be called in computer graphics perspective division. And then we shift that coordinate by 0.5. So what we are doing here is we are shifting our coordinate system to be, I think, in the center of the image with this 0.5. Okay, and then we are checking if u is greater than 0 and v is greater than 0 and u is less than wg at position 1. So our wg is in, we got that from the dataset loader, and then I also think from the photometric undistorter or somewhere like there. This is basically the image width as a global variable, and y, the 1, should be the second level in our image pyramid, but why is it the second level and not like the finest level? Not sure about that. So we basically check the bounds, check if reprojected point PTP is inside of the image bounds, i.e. 0 to width or height. So we check if u is less than w, so the width, and v is less than the height, and both at index 1. And if this is true, then we create a new float dist, which is equal to course distance map. And from that we get the forward warped id dist final, which is a list, it seems, into which we index using u plus wg at index 1 times v. And to that we add ptp at position 0 or at index 0 minus floor f cast to float the ptp at index 0. Very cryptic in my view. And to make it even worse, there's well, not a very nice comment here next, which tells us, note, the sh and so on and so forth, my type is used here. So I will not read out what is written here on stream, but I will change that into something nicer, which is maybe the not so nice my type is used here. We can guess. Yeah, unfortunately, you all can guess. Yeah. But I will still not repeat that. Okay, next we check if the dist that we have calculated above, if this is greater or equal to current min act dist times ph, our imager point, and then my type, which is the not so nice my type that is used here. Whatever this means, I think it will still remain unclear if this comment is telling that here. So if this distance is greater or equal to the current min act dist type times the my type, then we want to call the course distance map. From that we want to add into dist final the u and v. So basically the image feature, the feature point coordinates, which are expressed using u and v. We want to add that into the course distance map. And we also want to add that to our variable to optimize dot pushback. This to optimize is a vector which can be where values can be pushed back into, and we add this imager point, the ph, to this list. So we want to optimize this point. Okay. Okay, then we have this if statement, the outer if statement, where we check the bounds. So if this is inside the bounds, we do this part, and else you want to drop it. Which means we take the feature and then the status, and update it using feature status, and then outlier. And we also want to release the imager. Okay. This is the for loop finished, where we loop through all the frame hashings. We go through all the active frames here. We have finished this at this point. So next we want to optimize something. So we create a vector of type shared pointer, of type point hashing, where we store optimized into. We want to take this optimized vector and resize it to the size of toOptimize. toOptimize.size. So we have these two lists. We have optimized and we have toOptimize. Now we want to basically shift the data between those two vectors. And we first write a comment. This will actually turn imager points into point hashings. Okay. We need to check if multi-threading is active. Multi-threading. If multi-threading, then we want to call thread reduce dot reduce, and we call that using a function pointer, which will be provided by the boost library with this bind method or bind function, into which we pass the full system, a reference to the full system, namely the function activate points empty reductor, then the this pointer, and a reference to optimized, and a reference to optimize, and some placeholder variables like one. Oops, I didn't want to do that. Placeholders for 4 variables, and then we pass 0. We pass the size of this vector to optimize dot size, and we pass the value 50. Like this. Else we want to activate points empty reductor, and we just pass the reference to optimized and a reference to optimize. Pass 0. We pass the size of to optimize. To optimize.size, and we pass 2 zeros. So this function call is the single threaded version, and this thread reduce.reduce method is the multi-threading method. I think we already saw that at some other location. Okay, and after we have activated or passed the data types to the individual function that reduce them, we can now loop through all the points that need to be optimized. So we create a for loop of type size t, and we call the variable k. K is equal to 0, k is less than the to optimize dot size, and we increment k in each iteration. Then we store shared pointers to the point Hessian and to the imager point. So shared pointer of type point Hessian, which we call new point, written like that. New point in small letters is equal to optimized at location k, and we create a shared pointer of type imager point, which we call ph, and we initialize it to the value in to optimize at location k as well. So now we have two pointers that point to the kth value in the vector of optimized point Hessians and to the kth value in the vector of to optimize to the imager points. Now what do we do with them? We check something. So we check if the new point is not equal to the null pointer. So basically if it has a valid value, and if it is the null pointer, so if we cannot access it, we want to remove the imager point. We do that by calling ph, then feature, and then status, which is equal to feature status, and then valid. And we also want to update the point Hessian and release this imager point. So we call ph and then feature and then point, and in that we call mp ph, which is probably the point Hessian, and set it to set it equal to the new point, and then we release it ph feature and then release imager. We also want to call new point and then take data and with this preparation we can now loop through all the residuals. So we create a variable r which is looping over all the new point and then residuals. And for every residual it is calling energy functional and then insert residual r. So I'm not sure at this point why the comment says that we are removing the imager point, but we are still adding some residuals to our energy functional. So this is not really removal for me, but yeah, I will take that. So if the new point is not equal, or if it is okay, so if the new point is not equal to the null pointer, it is valid, so we can do stuff with it. But else, basically an else if the new point is equal to the null pointer, or the point Hessian or imager point last trace status is equal to IPS OOB, so out of bounds. Then we say pH feature status is equal to feature status outlier. And we also call pH feature release imager. I'm still not happy with this comment here. Remove the imager point. I will add a to-do for me. Something like this. So is this condition if true really removing the imager point? Check later. Okay. But with that, we are finished with the method called activate points multithreading and can continue with the next method, which is of return type void, full system, and then activate, it's called activate points empty reductor. So this is the one that we have already called several times, I think, in the code. And this will be implemented later. It will take several parameters. It will take a standard vector of type shared pointer, of type point Hessian, I mean, and we'll take a pointer to optimized. Then we have something similar, standard vector of type shared pointer, and this is of type imager point, and it's called to optimize. Then we have our integer min, integer max, and then we have a vec10 pointer called stats, and we have an integer tid. Okay, and here we need to store, or we need to store the frames that we have somewhere. So we create a vector of type shared pointer, of type imager point temporary residual. We call that tr, temporary residual, and we initialize that using frames.size, which is a function call, and the null pointer. And now we need to fill in the individual values. So we create a for loop. We loop through this data type, this data structure. We create the data type auto and create a reference to the current t, which is the temporary residual, but here only called t. And we loop over the tr entries, so the temporary residual vector that we have created before. And here we say we want to create a residual. Create residual. And we do that by defining this variable t, which is equal to shared pointer of type imager point temporary residual. And this will be initialized using the new keyword, and then calling imager point temporary residual. So this is a data type that we still need to implement at some point, but the constructor will not take any arguments, so this is fine. We just create this new imager point temporary residual and assign it to t, which will then automatically initialize this element in this list tr, because we are creating a reference to this individual entry in this tr vector. Okay, after we have filled in the individual imager point temporary residuals, we now loop through the arguments that have been passed here, like the minimum value and the maximum value. So we need to create a loop for that. So we create an integer called k, and this is initialized with the min value that was passed to this method. And yeah, this is the min value, and we check if k is less than the max value that was passed, and we increment the k value. And in each iteration, we say that we want to dereference the optimized array. So in this case, we get the individual values and not like the memory address. And then we can, from these actual values, we can get one specific value in this vector by using the k iterator variable. And we can now update this value with a call to optimize imager point, which needs to get past a reference to the optimize. It's actually not the reference, but it's again the dereferencing operator. And similar as before, we index with the variable k into this list to get the actual value here. Let me quickly look up what is expected here. So this is expecting an imager point, it seems. A shared pointer to an imager point. So this will generate a shared pointer to an imager point. Then we will pass a 1 and tr. So the other parameters are the minimum observations and the residuals. So the minimum observations is just 1, and this tr is the list of residuals, as is written here. So the imager point temporary residuals. Okay, so this way we are initializing all the values in this array of optimized point hashings by calling this method optimize imager point. Okay, so this is it with the method activate points empty reductor. And next we have another method in the full system called flag points for removal. What this is doing, it is first asserting the EF indices valid. So this is a boolean, as EF indices valid is a boolean. So if this is false, this assert will what will it do? Not sure. Ah yeah, okay, if this is false, then this assert will also be false and will probably lead to an exception. So we want to have this EF indices valid boolean variable, we want that to be true to have this method continue. And if it continues, we create a new standard vector of type shared pointer, of type frame hashing, which we call FHS to mark points. So the frame hashings to marginalize. Like this. And this vector is empty in the beginning, so we need to fill it. So we need to fill and initialize the values of FHS to mark points. So we create a for loop with an integer I is equal to 0, I is less than cast to int the frames dot size, and then we increment I, and here we check if frames at index I, and then frame hashing, and then flagged for marginalization. If this is true, in which case we say FHS to mark points dot pushback, and then frames at position I, frame hashing. So we take the frame hashing from the current frame and push it back to the frame hashings to marginalize points vector. Next we need to keep some statistics, so we define various integers for setting flags. So we have an integer flag OOB is equal to 0. We have a flag in, which is also equal to 0. We have a flag in, which is equal to 0, and we have a flag no res, which is equal to 0. And with these flags we can now go through all active frames, which we do with a for loop by defining an auto reference to fr, which will iterate over the frames, which is a field in this full system. So the full system has a memory of all the frames that have been processed. And for every frame we now create a shared pointer of type frame Hessian, and we call that host and initialize it with the current frame and then frame Hessian. Then we have a second loop, a nested loop, where we create a new iterator variable with a reference to feet, where we loop through the frame and then the features in this frame. So this loop is looping over all the features in the current frame, in the host frame. And what it is doing here is it is checking if the feet status is equal to feature status, and then valid. So if this feature is valid, and if feet point status is equal to point status, and then active. And after I have fixed this indentation, we now know that the current feature status is valid and the current feature point status is active. So we can now store the point Hessian in a shared pointer of type point Hessian, called ph is equal to feet, and then point, and then mpph. And with this point Hessian we can check various things. For example, if the point Hessian I depth, the inverse depth scaled, is less than 0, or the point Hessian residuals dot size is equal to 0. If this is the case, then we know that we have no residuals or I depth invalid. Let me rearrange that so it is in the right order with this with the if condition. So I depth invalid or no residuals. Like that. If this is true, then we have the point Hessian point status to be set with point status and then outlier. And we also want to set the feature status equal to feature status outlier. And we want to increment the flag no res plus plus. Or we want to increment this simply. Okay, else if pH is OOB. So if it is out of bounds, what is out of bounds? The frame Hessians to mark points, or host is flagged for marginalization. In this case, the point goes out of the boundary, or the host frame is marched, which means that we want to increment the flag OOB, and we want to check if pH is in layer new, which is a method of this point hashing. So if this is true, then we want to increment the flag in, which is the flag for the in layers. We have this integer n good res that we are introducing and initializing to 0. And we'll then have a for loop that loops over all of the point hashing residuals. So we create an auto data type. We call the variable r, which is looping over the pH and then residuals data type. And for every residual in this point hashing residuals vector, probably we will call r, so the residual reset OOB, so the out of bounds is reset. Then we have r linearize. It should linearize this, and then h calib, then mpch. Then it will also set the residual is linearized. Linearized to false, even though it linearized it before. Well, next it will also apply the res with the argument true. And it will then check if r is active, which is a function call or a method call. And if this is true, then the residual will call the fix linearization f with a passed this pointer to the energy functional ef. And we increment the n good res variable that we have introduced before this loop starts. And after this loop over all the residuals has finished, then we need to check several things. We need to check if pH idepth hashing is greater than setting min idepth h mark. So if this is greater than setting min idepth h mark, if this is true, then we know that the idepth is good. So margin it. Which means we want to first increment the flag in, and then we want to call pH point status and set this equal to point status and then marginalized, like this. Else we know that the idepth is not good, so drop it. pH point status, we overwrite that or update this to point point status out, which probably stands for outlier. Okay. After that, we have finished this if statement. So if pH is in layer new is now finished. But we need to check the other case, so else, which means not active, drop it. In which case we just copy the statement from before and say pH point status is equal to point status out. Okay, like this, and then we close all the scopes here. We close the for loop. And after this for loop, where we loop over all the frames, is over, we can log an info which tells us that flag no res is simply our flag no res, and we also add OOB, which prints out the flag OOB. And then we also want to print out the marged, which will print out the flag in. And then we end the line. Is it really marged? I need to double check that, just for completeness. Flag OOB, flag no res. Okay, so what flags do we have here? Flag in is missing, I think. Okay, so we print out the flag in, but we do not print the flag in, which seems to be fine. Okay, let's keep it like that. Even though I'm a bit confused about this flag in, which means that those are marginalized. Flag OOB, why is it flag OOB here? Okay, so the flag in is incremented here. After we have checked if the idepth Hessian is greater than the setting for the min idepth H mark. Interesting. So this is really quite confusing in my view. But that's how it is. Okay. Still about 700 lines of code to go, even though I'm here already at line number 1500. So this is a bit off to the original code because I have added more curly braces, I think, and more comments. This is just my style of programming, which is different to the original code base, and that's why we have this offset here. Okay, so let's continue with the full system method called make new traces. So here we are actually tracing out the points, and to do that we need to know in what frame do we need to do that. So we have a shared pointer of type frame Hessian, and this variable is called new frame, And we also pass a float pointer, which is called GT depth, which I always think is ground truth depth, but it probably isn't, but something different. Okay, so make new traces will now create the individual imager points, which will then be activated, and after activation will either be in layers or out of bounds or have any other state. Okay, so to make those new traces, we have several point selection strategies, and we need to distinguish them here. So we have an if condition, if setting underscore point selection is equal to 1, then we have something, else if the setting point selection is equal to 0, sorry, then we have something different. And we also have a third selection strategy. So we have an else if setting point selection is equal to 2. So these individual if blocks are depicting what we are doing, or they are defining what we are doing when a specific setting is set for the point selection strategy. Specifically, this means for the setting point selection equals 1 condition, we can log an info which tells us which one we are using. So here we are using the LDSO point selection strategy. End line. In the other one, so in the setting point selection is equal to 0, we are using the original, not LDSO but DSO point selection strategy. And if the setting point selection is equal to 2, we are in fact using random point selection strategy. Okay, so these are our 3 selection strategies, which mean that if we have a new frame that is coming in, this new frame hashing, then we now want to find, in this frame, we want to find specific corners or image regions or any other type of feature point that will then, during optimization, be turned into a 3D point. So every point in an image will have an associated depth, and this way we can back project this point in the image into 3D space to get a 3D point cloud. And this 3D point cloud will then yield our final map, and is one of the core ingredients in a Visual SLAM, besides the camera trajectory. And therefore we need to pay attention what kind of points we are selecting in the images, because different points will have different will influence the Visual SLAM in different ways. So I'm talking here about specifically, for example, if we are selecting a pixel that is not in a corner but on an edge, for example, we can basically slide this this feature point along the edge, and this way we cannot really associate those points across an image sequence to a very unique point, but it will probably move along this edge, and this is also called the aperture problem. Okay, so we need to implement the point selection strategies here, and we will do that in this method. So we begin with the LDSO point selection strategy, which begins with the new frame that was passed into this method. We get the frame from that, and from that we get the features array, and we want to reserve a specific number, which is a setting that we can set. So we just pass the setting desired image density. So this is basically the number of feature points we want to detect in one image. With that, we can now call the detector dot detect corners, and this needs to know, well, how many corners do we need to detect. So we pass the setting desired image density, and we also pass the frame in which we want to detect the corners. So we pass new frame and then frame. With that, we can now loop over all the image, like the corners, with a for loop. We create a data type auto and a reference to feet. And we loop over the new frame and then frame and then features data structure. Here we want to create an imager point, which means we want to create an imager point for like every feature in this frame. So we say for the current feature that we have, we get the IP, which is the imager point, and we initialize it with a shared pointer. A shared pointer of type imager point. And the imager point is initialized using the shared pointer needs to be initialized with the new keyword, new imager point. And the imager point is then initialized using a new frame and frame. So the imager point needs to know to what frame it belongs. It will need to know specifics about the feature, and it will need this one, which I will tell you in a second what that is, and it needs the H calib and then the MP calib hashing. So the camera calibration is also needed. And what is the one? Let me quickly look that up. It is telling that this is the type. So this one is a type. And maybe let me quickly look up what this type means. The type, my type. Ah, okay, this is this weird my type, it seems. Oh, there are Chinese comments here in this file. Interesting. Okay, let's skip that for now. So each imager point can have a specific type. What this my type is then telling us, we will see that in a subsequent part in this live stream. Okay, after we have looped over all these feature points and initialized them, we can now print an info by calling log info and then printing new features created. So new features created, and here we print new frame features dot size end line. And this is the whole code for the point selection of using the LDSO point selection strategy. Next, we are continuing the original DSO point selection strategy. For this, we need to have the pixel selector and set the allow fast to true. Okay, with this we can store the number of points total, which we can get from the pixel selector, and then calling make maps, where we pass the new frame and the selection map. A selection map. And of course, as before, we need to pass the setting that tells us what is our desired image density. So our total number of feature points that we want to detect in the image, in the new frame. Okay, after that we call new frame features dot reserve. And what do we want to deserve? We want to not deserve but reserve the num points total. And I have a typo here. I want to reserve this number. After that, we have prepared the number of points that we want to create. So we now need to loop over the image, and we do that using two for loops. So I will create those two for loops, and the first one is the y coordinate, which is equal to pattern padding plus 1, and loops until y, or while y is less than hg at level 0. So this time we take, I think, the finest level in the image pyramid and take the height from that image, and we want to make sure that y is inside this this height boundary. But we subtract pattern padding from that, -2. And we increment y, and this is our first loop statement. And the second one, as you might have already guessed, is that we continue with the x coordinate, which is equal to pattern padding plus 1 as well. And then we have x is less than wg, so the width of the image, minus pattern padding -2, and then we increment x. Okay, so here we are looping over y and x, so the both directions in our image space. And we now need to store the current index, so int I is equal to x plus y times the width in global, like the global variable, at level 0. So this is like the sequential. We are basically taking the image, the 2D image, and linearizing it into a 1D vector, a 1D array. And we can now take this index I and loop or access every like single pixel of the image. But before we do that, we need to check if the selection map at index I is equal to 0, which means that here we will continue. So the selection map is, it seems, a field of the full system, and it has the same dimensions as the images, so it has like the WG and HG as the image dimensions, and it will have values stored with 0, which means that we basically do not want to detect a feature there or a point. We do not want to select a pixel there. Something like a mask, I would say. This seems to be a mask that tells us, do we want to have features there or not? Okay. After we have successfully found out that the selection map is not 0 at the current index, we can create a shared pointer to a feature which we call feed, and this will be initialized using new feature, and the feature takes in an X and a Y and a frame. New frame and then frame. This is how a new feature is initialized, and with this new feature we can now call feed IP, which is the imager point, and set this one equal to a shared pointer to an imager point, which we initialize using the new imager point call, and this will take in the new frame, so it will take in a frame, will take in a feature, and it will take the selection map at index I, and it will take the hcalib mpch, the calib hashing, the camera calibration. So this imager point, we initialized it here as well, and here we have passed 1. Whereas in the original DSO point selection strategy, we pass in the selection map at index I. Which means that this selection map will usually contain values that are not 0, because the 0 we have checked for that in this line of code. So probably this will always return a 1, but maybe there is also the possibility that the selection map will also have different values different than 0 and 1, maybe 2 or 3 or something, which can have a different meaning. So this is something we need to pay attention when we are implementing the imager point data structure. Okay, so here we are initializing the feature imager point using this shared pointer. And after that, we need to check something. If not standard is finite, the feature imager point energy th, maybe threshold. If this energy threshold is not finite, then we want to call feed, release all, and continue. Else, we want to call new frame features dot pushback. We want to push back the feature into the list of features. Okay. So now, after we have finished the two for loops here, we want to log an info that tells us new features created. I think I will change that later with this features. New features created, and then we want to print out the new frame features.size, and then end the line. Okay, and this is it with the DSO point selection strategy. Now we need to finish the third variant, which tells us that we are using a random point selection strategy. And this means we need to call CV, the OpenCV library. And from that we have an RNG, a random number generator, which we call RNG. And here we start with, again, reserving the space for the features that we want to create. So we say new frame features dot reserve. I want to reserve based on the setting desired imager density. Like that. And then we have a for loop that loops with an integer I is equal to 0. I is less than, what is the count? The count is the setting desired imager density. And then I++. Here we need to create like the coordinates that we want to, where we want to put our feature in. So we have an integer x, which is equal to rng.uniform. So we have a uniform sampling in the range of 20 to wg at index 0, so the width of our image minus 20. And this is it. So this will yield a value, an integer to be specific, in the range of in between 20 to the image width minus 20. And then we will have an integer y, which is equal to rng.uniform as well, and similarly 20, and then hg at index 0 minus 20. This way we have x and y values that are randomly picked, and with this we can create a shared pointer to a feature, which we call feed, and then we initialize that using new feature, and a feature needs an x, a y, a new frame, so basically a frame, and then it is happy, a happy little feature. And with this feature, we can then initialize the imager point. So we can call feed IP and set it equal to a shared pointer of type imager point, which we initialize using the new imager point, which needs the frame, new frame, and a feature that we have created before. Then we need to pass the type, which is 1 in this case again, and we need to pass the camera calibration hcalib mpch, the calib Hessian, like this. After that, we need to check if not standard is finite. Feed the feature, then imager point, and from the imager point the energy threshold. If this is not finite, then we need to call feed release all with a semicolon, of course, and we continue. Otherwise, so else, we call new frame features dot pushback, and we push back the feature. Okay, with this for loop completed, where we are just creating this number of random points and creating them here, initializing them, and adding them to the new frame features list. After that is finished, we can log an info, and I will not type that out, but I will copy that from here. Like this. Okay, and this will finish this method called make new traces, where we will actually create the points that are being used to create the 3D point cloud, the 3D map, within this Visual SLAM system. And I will now fix this one. I will just delete one of the features here. New features created, and new features created. I think that's sufficient. Alrighty. Next, we need to create a method called initialize from initializer. This will take in a shared pointer of type frame Hessian, new frame, we call that new frame. And we now need to lock the map mutex again using a unique lock. Unique lock of type mutex. And we call the lock, and we lock the map mutex. Then we need to create a shared pointer of type frame Hessian, which we call first frame, and this is equal to course initializer, and from that we can get the first frame. Then we have a shared pointer to a frame where we say fr is equal to first frame and then frame. And we also want to set the first frame IDX, the index, to be equal to frames.size. like this. After that, we want to take the frames and push back the current frame, FR. We also want to set for the first frame the frame ID to be equal to global map and then num frames like this. Then we have our energy functional, in which we can also insert a frame, insert frame, and we pass the first frame and the camera calibration, hcalib, and from that mpch. And then we want to set precalc values, which is a method in the full system, it seems, that will initialize values for us. Then we have the frame, and we call for the frame the features dot reserve. And what do we want to reserve? We want to reserve the width as the global variable at index 0 times the height for the images, but this one multiplied with 0.2f. So we take 20% of width times height. Image width times height. Why? I don't know. But this is how it's done. And then we will introduce a floating point number called SumID. And this is initialized with 1e to the minus 5. So a very small value, close to 0, and a numID, which is also the same value, 1e negative 5. So we have a SumID and a numID, and we will use that to count the number of points and the number of IRs. We will see. So we have this for loop where we loop through using the int I is equal to 0, I is less than, we loop through the course initializer, and in the course initializer we have num points at index 0, and we increment I. And in this loop, we say SumID. We increment that using course initializer and then points at index 0 and at index I dot IR. Let me see if I can find out what IR is. So this is simply the point IR. Okay, so this is a data structure called PNT, which is the point structure used in the course initializer. And this data structure, it just has a float, which is called IR. And this is unfortunately not explained what this is. So I'm not able to tell you that at this point. We will need to find out once we are implementing the course initializer data type. So let's continue with the numID. And the numID is simply incremented here. So the difference is the numID is incremented by looping over all the num points at index 0, and the SumID is incremented using the value of the point data structure namely this IR, this mysterious IR value, as the incrementation value. After that, we have the float that we define as a rescale factor, which is equal to 1 over the sum ID over the num ID. Which is another addition of a confusing thing, in my view. Yeah. Okay. After that, we want to randomly subselect the points I need. The points I need. We do that by defining a float keep percentage, which is equal to setting desired point density over the course initializer, and then Ahomo, heading out. Thanks for the stream. Thank you for watching, and have a great end of the day or beginning of the day. See you soon. Thanks for watching. And the music is out. Course initializer num points at index 0. So this is the keep percentage. So we have the desired point density and we have the actual point density. And this ratio is the float keep percentage. We can print that out now. So we can say log info. And we start with initialization. Keep 100 times keep percentage. And then we print need. What do we need? We need the setting desired point density. But we have what do we have? We have course initializer num points at index 0. And don't forget the exclamation mark, and then we end the line. Okay, like this. And after that we create features in the first frame. We do that by creating a for loop of type size t. I is equal to 0, and I is less than size t of the course initializer num points at index 0 and I++. Here we now check if rand, like the random generator, over cast to float, the rand max is greater than keep percentage then we want to continue. If not, then we want to create a PNT, which is a struct which is defined in the course initializer, PNT, pointer to a point, and we initialize it using the course initializer, and from that we take points at index 0 plus I. So this is basically, I think, pointer arithmetic, that that we get the first point in the points array and just add this number to move in the memory address to the desired point that is sitting at index I. So I think we could also just add this or move this I into this access into like this data access here. So replace the 0 with I. But I mean, that's perfectly fine like this. Then we create a shared pointer of type feature, which we call feat, and then we initialize it with new feature, and we pass point u plus 0.5 f, and we pass point v plus 0.5 f, and we pass the first frame. Like this. Then we call feat IP, the imager point, and set it to a shared pointer of type imager point, we initialize it with new imager point and pass the first frame, the feat, the point, and here it is, the my type, mighty my type, and we pass the camera calibration hcalib and then mpch like this. So similarly, like we have seen it before, we are just creating new feature points here. Yeah, and next we check if not standard is finite, feature, imager point, energy threshold. If this is not finite, then we say feat, release, imager, and continue. I have the feeling that I have seen this kind of code sequence before, so this can probably be moved into a specific function, yeah, to optimize it a little bit so that there's no code duplication. After that check, we say feat create from imager, and we create a shared pointer to a point Hessian, call it ph, which is equal to feat point mpph, and we then check if not standard is finite, pH, energy threshold. Then we again call feat, release, but this time not imager but map point, release map point, and continue. And after that we say feat release imager. Why is it imager? Okay. Release imager because no longer needs the imager part. Okay, so we do not need the imager part at this point anymore. And we say the current frame features, and then pushback feet like this. And then we say point hessian set eye depth scaled point IR times rescale factor like this. pH set eye depth 0. pH eye depth. And we also need to set the pH has depth prior, which is equal to true. We also need to set pH point status is equal to point status, then active. And lastly, we need to set pH and call take data to set the eye depth into optimization. Okay, here we have for every num points at index 0, for every point in the course initializer, we have created such a point. We have created an associated feature, an associated imager point, and basically initialized the feature and the point hessian. After that, we need to create a new SE3 first to new transformation and set it equal to course initializer, and then this to next. Then we take this first to new and update the translation vector. Translation. We update it by taking the value and dividing it by a rescale factor. Which we have introduced before with this 1 over sum ID over num ID. Okay, now we say really no lock required, as we are initializing. So we only need those locks, those mutex locks. No mutex lock required when we are changing values that are used elsewhere. But when we are initializing, we are creating those values for the first time. So at this point, we do not really need a lock here, but it's still used as I see now. So let's create this unique lock. Unique lock of type mutex, which we call crlock, and we pass shell pose mutex. And with this lock we can now call first frame set eval pt underscore scaled, and this needs to get a pose, so fr get pose, and first frame, and from the frame the affine G2L lighting parameters. Or actually it's not a lighting, but it's like the light parameters, like the image brightness. And then we continue with new frame. We get the frame, and from the frame we set the pose to the first two new pose that we have modified above. And we also set new frame and then set eval pt scaled to new frame get pose, and new frame f G2L. Okay, so we have a first frame and we have a new frame. We need to initialize both of them, which we are doing here. And after this is done, we can say initialized is equal to true. This initialized variable is a field of the full system. And we can also say in this full system we have the global map. And here we want to add a keyframe based on the fr value. And after that we want to log an info to the console, which is called initialized from initializer points first frame features dot size, and then we end the line. And this is actually it with this method initialize from initializer. Okay, now that I have taken a drink, we can continue with the next method, which is called remove outliers. This will return void. It's in the full system, and it will be called remove outliers. It will not take any arguments, but it will simply keep track of the num points dropped, which is 0 in the beginning, and then we will have a nested loop for auto and fr. So this is the frame, it will loop over the frames. And in this loop we have another loop which loops over the features, feet, in fr features. Of course we need this arrow operator. And in this inner loop we check if the feet status is equal to feature status valid and feet point So if we have a feature point, and if the feed point status is equal to point status active. If all of this yields the final statement to be true, then we will have a shared pointer that we will create of type point Hessian, call it ph, which is equal to feed, and then point, and then mpph. And now we can use this point Hessian to loop over, not to loop over, but to check if ph residuals dot empty. If we do not have any residuals, then we say ph point status is equal to point status outlier, and we also have the feed status, which is equal to feature status to be also outlier. And we also need to say that we are dropping this current point, and therefore we need to increment num points dropped by 1. After this, those two loops have completed, like looping over the frames and over the features, we can log an info to the console, which tells us remove outliers done, outliers, and then we simply print number of points dropped and end the line. But we also need to call the energy functional, and there we need to call the method drop points f. Like this. Okay, the next method is called set precalc values. We have seen that before. Now we are implementing it. It's in full system and called set precalc values. It takes no arguments, and it will loop over the frames. So we have a reference to fr, and this will loop over the frames. And the first thing that is happening here is we call frames, or the frame, and we get the frame Hessian. And then we get the target precalc object and resize that. We resize it to the frames.size. After that, we can create a for loop with size t. I is equal to 0, I is less than frames.size, I plus plus, and here we say fr frame Hessian target precalc at index I dot set, and we set it to the frame hashion, and we pass in the frames at index I, frame hashion, and we pass hcalib mpch. Like this. So that now we have set the target precalc array, we have resized it to the frames.size, and we have initialized every single element by looping over all the frames.size that we have, by setting the target precalc values to the current frame hashion, and to the frames at index I, frame hashion, and the camera calibration. After we have finished those two loops, we call ef energy functional set delta f, and we pass in the hcalib mpch, a camera calibration as well. And this is the set precalc values method. Next we have another void full system method called solve system. And this will take in an integer for the iteration and a double called lambda. And this is calling the get null spaces method that should be implemented in the full system as well. I think we do not have it yet. And the return type of that will set the energy functional last null spaces for logging. So we set that one equal to get null spaces, and this get null spaces method needs the energy functional last null spaces pose. It will also need the scale, and it will need the FA and FB, affine light parameters. After that, we call energy functional solve system f by passing the iteration, the lambda, and the hcalib, and then mpch. And this is the method solve system. Next method that we have is the linearize all method, and this will return a vec3. So vec3 full system linearize all. This will take in a boolean called fix linearization, and this one will be a longer method First we define 3 doubles. The first one is called last energy P, which is equal to 0. Next one is last energy R, is also equal to 0, and we have a double called num, which is also equal to 0. Then we have a standard vector of type shared pointer of type point frame residual, and this one is called to remove, and number of elements will be num threads, which is, I think, a variable defined in the beginning of this file. Okay, probably not. Maybe in the header file. I think I saw it somewhere. Okay, this one is max active frames. I think I saw it somewhere, but probably not in this file. Maybe in the settings, but it doesn't matter anyway. Okay, after we have initialized the or not initialized, but created the space for the to remove vector, we now need to initialize the values. So we say for int I is equal to 0, I is less than num threads, I plus plus. Then we call for each element to remove at index I, we call clear. Next we need to check if we have multi-threading. If multi-threading, then we call thread reduce dot reduce, and we pass on again this bind function to the full system, and there we pass linearize all reductor. We pass this and fix linearization to remove, and the placeholders 1 through 4. And we also need to pass the 0 and active residuals dot size and 0. We finish this with a semicolon, and we also need to update the last energy P to be equal to thread reduce dot stats at index 0. To store what the reduced thread is returning here, the linearize all reductor. Okay, if we do not have multi-threading, then we need to create this stats vector as a new object. And then we just call linearize all reductor without the thread reduce. And we still pass the fix linearization. Fix linearization to remove 0 active residuals dot size, and we pass a reference to the stats vector, and we pass a 0. So the signature of this linearize all method is something like, here is a minimum value, here is the minimum value, here is a maximum value. This one takes a vec10 of stats that we have defined here, and the last value is a TID, which is 0 in this case. And we also need to update the last energy P, which is in this case equal to stats 0. And I should mention that this, okay, as it already is depicted here, the vec10 is just passed as a reference. So this method is then filling up this vec10 here, so we can access the 0th element to tell us what the last energy was that was calculated in this linearize all reductor. Okay, after the check for multithreading, we need to set new frame energy, th. This is a method that we can just call globally in this full system. It will set the internal data structures. Then we can check if we want to fix the linearization. Then we need to loop through or loop over auto R over all the active residuals. So one R is an active residual. And here we can create a shared pointer of type point hashing, call it ph, which is equal to r point.log. And then we can check if the point hashing last residuals at position 0 dot first is equal to r. Then we want to say, or to set ph last residuals at index 0 dot second is equal to r state, yeah, and that's it. And else if actually ph last residuals at position 1 dot first is equal to our current residual. Then we want to set ph last residual at position 1 second is equal to r state, like this. After this first loop, we want to keep track of the number of residuals probably removed, which is 0 in the beginning. Then we start a nested loop with int I is equal to 0, I is less than num threads, I++, and inside this loop we have another one which loops over the active residuals. No, actually it will create an auto R and loops over to remove at index I. So this to remove was created before based on the number of threads that we have. It was initialized using those either thread reduce or linearize all reductor methods. And then we can loop over this in this for loop. And now we need to remove that. So we store the current point hashing in a shared pointer. Shared pointer to a point hashing. We call it ph. And initialize it with the current residual that we want to remove. So r point.log again. And then we do it similarly like before. So I copy that part. And let's double check it. So we have the point hashing again. And we call the last residuals at position 0. First is equal to 0. And if this is true, so if the current residual is equal to the last residuals at position 0 and the first from that, then we want to override that. We want to say ph last residuals at position 0 dot first is equal to simply 0. And we do the same with the last residuals at index 1. So if the first one is also equal to the current residual, then we want to override this first with a 0 as well. Like this. But after that, we need to call energy functional drop residual, and we need to pass R to it. And this will actually remove the residual. Then we have number of residuals removed incremented. Now we are finished with this if block. If we want to fix the linearization, so that now we can return from that function. And remember, this linearize all method will return a 3D vector. So we need to return a vec3, which we initialize using 3 values. The first one being the last energy P. The second is last energy R. And num. And with this, we have finished the linearize all method. And we can now continue with the linearize all reductor that we have called here and here. So we need to implement that because it's a member of the full system. So we have a return type void. We have it in the full system, and it's called linearize all underscore reductor. It will take in a boolean called fix linearization, as you already saw, and it will take in a standard vector of type shared pointer of type point frame residual, which is a pointer to the vector which is called to remove. Then we have an integer for the minimum values, for the maximum values, and we have this vec10 pointer called stats, and we have an integer for the TID. And then we start with the body of this method, and we have at this point 500 lines of code to write left, so we are slowly moving towards the end of this FullSystem.cc file. And I'm really hoping that I can finish it in this part, so that we can, in the next part, try to make this full system functional. So let's continue. We start with a for loop, and this for loop will have the integer k as the iteration variable. This will be initialized using the min value. Then the check is if k is less than max, and k is incremented. In the body, we will have a new shared pointer of type point frame residual. It is called R for residual, and is equal to active residuals at index k. Then we take the stats variable, the vec10 that was passed, we dereference it, and we take the first element from that, and we add to that the residual. From the residual we call the linearize method that needs to have the camera calibration, hcalib, and then mp calibration, ch. Then we need to check if we want to fix the linearization. Then we need to call the residual, and from that we need to call the method apply res with the parameter true. Then we need to check if R is active, so this residual can be active, and if it is, then we also need to check if R is new. And if it is new, then we need to create a shared pointer to a point Hessian, which we call P, and set it equal to the residual point.log. And we do the similar with the frame Hessian. We will have it twice, because we have a host frame and a target frame. So we have the residual, and then we have a host.log, and we have a target.log. And next we have a vec3f called ptp inf, which is equal to host and then target precalc. And from this target precalc vector we take the target idx, and here we take the pre underscore krki, we know that from before, so this is the calibration matrix times the rotation matrix times the calibration matrix inverted. But here we have an additional TLL, and this is multiplied with a new vec3f, which will be initialized using the point Hessian. From the point Hessian we take u and we take v, and we set 1 as the third component, which again looks like a homogeneous coordinate. We can add a comment to that. Projected point assuming infinite depth. So we will have this ptp inf, which is a projected point with infinite depth, but we will also have another one, which is a simple ptp without infinite, which is the ptp inf plus host target precalc target index, and then dot pre. And then we do not have the same here. We have only kt, that's an R, that's an T, kt TLL times, in this case, we have the point Hessian P. From that we take the idepth underscore scaled, and this is the projected point with real depth. Next we need to create a relative BS, or I don't know if it's relative, but it's probably relative. We set it equal to 0.01 times. Now we access the ptp infinite, and from that we take the head. We take 2 elements from the head. So I think this is basically the first 2 values in this whole vector, in this 3D vector it seems. And we divide the values by the ptp inf at position 2. So we divide the first 2 coordinates by the homogeneous coordinate. If it is 1, which it will probably not be after this calculation necessarily with the multiplication of this matrix, we simply divide it by the homogeneous coordinate. We do a normalization, we could also say. And we subtract that by the PTP, by the normal PTP head, the first two elements from the head divided by the PTP at index 2. So similar, we also divide by the homogeneous coordinate. Then we subtract the two vectors from each other, and we take the norm of that, like this. And we comment that by writing 0.01 is equal to 1 pixel. So this is why the 0.01 value, where this is coming from. Okay. Next, still inside this if R is new condition, we say if rel bs is greater than p max rel baseline, so the baseline is basically if you have two images, two frames, it is the distance between those two frames. So this is why the norm is taken here. Which should yield me the distance as a float. So if this calculated relative baseline is greater than the maximum relative baseline that was defined for the point Hessian, then we need to clamp that to this maximum value. So we need to say, we do not clamp it, but we update the maximum relative baseline. So we say point Hessian, then max rel baseline is simply equal to the currently calculated relative baseline. And after this if statement, we also want to increment the num good residuals in this point Hessian by 1. Okay, so if the residual is new, is finished now, then we have this other if statement, if R is active. And this if R is active, this will have an else case. So we add an else, which will then call the to remove list at index TID. And from that, we push back the active residuals at index K into this vector that we want to remove that. Okay, and this is it with this method called linearize all reductor. Okay, next we will have a method that we will comment. So this applies step 2 linearization point. So this will return a Boolean value, and this method is called FullSystem.do from backup. It will take in a float for the step fac c, and various other step factors. We'll have a step fac c, step fac t, a step fac r, and a step fac a, and lastly a step fac d. Cryptic names, we will see if we can find out what they mean. First we will create a vec10 with the p step fac. So this will probably hold all of the step factors that we have. And we'll see that in a minute, because here we set p step fac dot segment. So we take 3 elements starting from 0 and set those 3 elements by a constant, namely using step fac t. So this could be the translation vector, which is a 3D vector. And then we have the segment starting at 3, at index 3. We set the constant using step fac r. And the last one will be a segment with 4 elements and starting at 6. So here we need to add 3, here as well. And from index 6 we have 4 more values, which we initialize using step fac a. Next we create new floats for sum a is equal to 0, and we add the other ones as well, sum a, sum b, then we have sum t, sum r, sum id, and we have a num id, which is also equal to 0. Then we have a float sum nid is equal to 0 as well. And now we are checking if the setting for the solver mode is, if we combine it with the solver momentum, if this is true, the combination, then we set the value in the camera calibration hcalib, then mpch, and then set value hcalib mpch value underscore backup plus hcalib mpch step. So we are initializing the mpch with a value based on the value backup and the step. We can now start a for loop where we loop through all the frames that we have. So auto data type reference to fr, looping over the frames. Now we need to store the frame hashing, so we create an auto. FH for frame hashing is equal to FR and then frame hashing. And then we create a 10D vector called step, which we initialize using the frame hashing step field. Then we want to update the step head. Namely the first 6 elements of that. We want to add something to this, to these 6 elements. We want to add 0.5 f times the frame hashing step backup dot head, the 6 values from that. Then we need to call the frame hashing and set a state, set state, fh state backup plus step and then we update our sum values that we have defined above. So we have sum a is plus equals step at index 6 times step at index 6 again. So basically the step at index 6 to the power of 2, a quadratic value. With b it's the same, but with a step at index 7. And with t we increment it by getting a segment from a step, from the step, with 3 values starting at 0, and here we want to have the squared norm. And similarly with the r, sum r, we have 3 elements again, but starting at 3, at index 3, with squared norm as well. After that we have a for loop, where we loop over the features in the current frame. So we have an auto, feed, and we loop over fr features, where I'm wondering why this feed is not a reference. This should, I think, be a reference, because in the next line of code it is used as a reference. So therefore I will add a comment Okay, so this is something that can be fixed later. Currently, I do not want to change anything to the original code base. So I have this auto feed in the features of a frame, and then we have this if feed, and here we have this reference operator, this arrow, which brings me to the opinion that this should be an AND here, like a reference operator. Okay, if feed status is equal to feature status valid with 1L and feed point and feed point status is equal to point status active and here we store the point hashing ph. We get that from the feature and then we get to the point, and from the point can get the MP point hashing. Then we have a float step which is equal to point hashing step plus 0.5 f times point hashing step backup. Then we have the point hashing where we can set the I depth, the inverse depth I think. Point hashing I depth underscore backup plus step. Then we have the sum ID which we increment using step times step as the incrementation value. Then we have sum NID which is also incremented using another value FABSF of point hashing I depth backup. Then we have num ID, we can increment that. Then we have the point hashing set I depth 0 ph I depth backup plus step. And this is it with this for loop and the if statement inside that. And this is also this for loop where we loop over the frames. This is also finished. And now we have this outer if statement. We have checked for the solver mode. So if we have this specific solver mode of solver momentum, then we do this. But else, we do something different. So we have our hcalip. From that we take MP calip hashing. And here we set value using the hcalip. And from that mpch again, the calip hashing. From that the value backup plus step fac c times hcalip mpch and then step. Like this. Then we have the for loop as above. We create an auto variable called fr. We loop over the frames. And here, interestingly, here there is a reference. But above, okay, here is the reference, but here there was no reference. So, okay, for the frame there is a reference, but for the feature not. Let's see if there is a reference for the feature here. The first thing we do here, again, is we store the frame hashing. We get that from the frame and then frame hashion. Then we call frame hashion set state using the frame hashion, and then state backup plus pstepfag.cwise product. We pass the fh step vector to the component wise product. And then this line is finished. Then we have the same sum a, b, t, and r values. Besides that, we have the frame hashion from which we get the step variables. Like this. And then we have this for loop where we loop over the features. So we have an auto feed fr features. And here, in fact, it is really not the feature is not referenced, but it is like written like that. So I will also add the same comment here, just in case I will decide to change that later. I will probably need to do that in this part as well. So this way I will not forget it. Okay, so for every feature now, we want to check the status, if the feature status is valid and the point status is active. For this, I will simply copy this part and then I will check if something's different. So if the feature status is equal to feature status valid, and the feature point is defined, and the feature point status is point status active, then we want to create a point hashion, which we get from the feature point and mpph. Then there is no step here in this case, but we call the point hashion set the inverse depth to point hashion idepth backup plus, and here we get the step fag_d times ph step. The sum ID is added to itself with step times step, but we do not have the step, but we have the point hashion step like this. So this one squared. Then we have sum nid plus equals fabsf ph idepth backup. Then we increment numid and we set the point hashion idepth 0 based on the point hashion idepth backup, but here we have step fag_d times point hashion step. And with this we are finished with the else block. And we can now update our sum A values by dividing them with the frames.size. And not only sum A, but also the other ones. So we have sum B and sum R and sum T as well, which are all the same. Then we have sum ID, which we divide by the num ID. Then we have sum NID, which we divide by the num ID as well. Then we have our EF delta valid set to false. And we will call set precalc values. And we will return the square root as a float, because what will this method return? It will return a boolean, so we need to concatenate checks using the squared root of sum A. We want to check if this square root is less than 0.005. 10, I'm missing 10, so 0.0005 times the setting for the threshold opt iterations. And next we add another square root and another one and another one. The second one is related to the sum B, and this should be less than 0.00005 times the setting opt iterations. Then the third one is sum R. It should be less than 0.00005 as well, with the same setting. And then we have sum T times, so the square root of sum T times sum NID, which should be less than 0.00005. So the same as above, with the same setting multiplication here. And this is the whole return statement, which will then return a true or a false, depending on if this if these values that have been calculated are less than those settings. Okay. This is the method do step from backup completed. Now we need to implement the backup state method. So we have the full system, and in this we have a backup state which gets a boolean passed called backup last step. Here we will check if the setting for the solver mode and with the bitwise end of solver momentum, if this will return true. Then we check if we have this boolean backup last step set to true. So if backup last step is true, then we want to update the hcalib mpch. So the calib hashing, it will have a field called step backup, and we set it to hcalib mpch step. Then we have hcalib mpch value backup. We set that to the hcalib mpch value. Then we have a for loop. We loop over all the frames. So we have this auto data type, we have a reference to the current frame, and we loop over the frames. We have a frame hashing that we need to get. So auto fh is equal to frame and then frame hashing. Then we say fh step backup is equal to fh step, and fh step, no, not step, but state backup, easy to confuse, is equal to fh get state. Then we begin a nested loop. We loop over the features where we again do not have this reference operator. So we write auto feed fr features, then we need to check if the feature point is set, and the feature point status is equal to point status active. So if this evaluates to true, we create a point hashing auto ph is equal to feed point mp point hashing. Then from this point hashing we set the idepth backup equal to point hashing idepth, and the point hashing step backup we set to point hashing step. Like this. And I will copy that comment from above just in case. Probably it's not necessary to reference this feature point as is done with the frame, because we probably do not want to modify the features in this frame here, whereas we want to modify the frame hashing in this frame object here. But this could easily also be an unwanted side effect, so it's better to double check that at some later point in time, when there's time for that. Usually we do not have time for these like details in the implementation, but at least it's worth to mark that as being something which is, I would say, a little bit weird about the code. Or not weird, but probably something unusual compared to the other lines of code that we have, like here, for example. Okay, so we did the step backup and idef backup to the point hashing. We have closed the for loop, the inner for loop. We have closed the outer for loop. And then we have this if statement here that checks if we have the backup last step set to true. But if not, then we will do something similar. So let's copy that code. And let's go through it. So if backup last step is not set or not true, then we want to initialize the step backup simply by calling the set0 method. The second line will stay the same. I'm already saying step instead of stay, which is the influence of the code, it seems. Now we are looping over the frames as usual. We get the frame hashing from the current frame. Then we have the step backup, which we now just set to 0. Set 0 as above. But the state backup, we can get that from the frame hashing. Then again we have this for loop where there's no reference here, but we loop through the features in the frame. Then we check if the feature point is set and the feature point status is point status active. In which case we create a new point hashing from the feature point mpph, and here we have the point hashing idef backup set to ph idef, and the ph step backup, this will be set to 0. Okay, and with this we have finished this outer if statement for the solver mode solver momentum. But there is an else case which is like that. So we have this hcalib, our camera calibration. From that we get the mp calibration, and from that we get the value backup, and we override that using the hcalib, mp calibration, and then value. Then we have a for loop, a loop over the frames in the full system. So auto and the reference to fr, we loop over the frames. Then we have a frame hashing that we will define using the frame, and from that the frame hashing. Then we have the frame hashing state backup, which we override using fh and then get state. Then we have a for loop with auto feed fr features. So we loop over the features again here without this reference. So I will copy that code here, this comment I mean. Auto feed in FR features. Then we check if feed status is equal to feature status valid and feed point status is equal to point status active. Then we want to call feed point status and check if this one, no, we already have that, I'm sorry. We have this in this if condition. Here we want to create a point hashing, which is equal to feed point mpph. And then we want to use this point hashing to update the idepth backup to be the point hashing idepth. Okay. Now we have the next method after finishing this backup state, which is called load state backup, which is probably the typo that I already noticed when writing this full system header file. But I will still write it out with this typo. So full system load state backup. But I will see if I have added a comment here in this header file. Load state backup. Here. We'll copy that to not forget edit or modifying the CC file. Okay, what is being done here? So we have our hcalib, our camera calibration, mpcalib hashing. We set the value to hcalib and then mpch value underscore backup. Then we have a for loop with auto fr in frames. Then we have auto fh is equal to fr frame hashing. Then we have fh set state, fh state backup. Then we have a for loop again, which loops over the features. Auto feed fr features. And interestingly, now there's no reference operator here in this feed, but also not in this fr. So it seems I really need to double check what influence adding this reference operator or reference modifier will have on the functionality of this function. If this will introduce any unwanted side effects, then of course we want to leave that out. So this needs to be investigated with several experiments, I would say. So if the feature point is there, and if feature point status is equal to point status active, if this is true, then we create an auto point hashing and set it equal to feed point mpph, and then we use this point hashing to set the idepth to point hashing idepth underscore backup, and we use the point hashing to set idepth 0 to point hashing idepth backup as well. Then we close the if statement, the loop, and the other loop. And after that we have ef delta valid, which is set to false. And we call set precalc values. And for completeness, I will now add the comments here for the for loops here. So like this. So feed should be and feed, I believe, and the same is true for this frame. Okay, so this is a check I will need to do at some point. But for now it's fine. It should work after all, because the original code is also working, so there's no reason why it should like destroy something. But the question is simply, why is that written like it is? So in my version of this full system, I have reached 2000 lines of code, whereas in the original code base I have still 300 lines of code left. So yeah, we are almost there, but it will still take a little time to finish this full system. But we're getting there. This is the good news. The next method will return a double and is called calc L energy. We'll also have as a next method, we'll have a similar one, which is called calc M energy. And they are also quite similar in the body, in the function body. So if a setting force accept with 1c step, if this is true, then we return 0, and else we return energy functional calc L energy f underscore mt for multi-threading, I believe. Okay, let's copy that and let's paste it here. Here we have the similar start, but the last line is energy functional calc m energy f without underscore mt. Okay, next we have a larger method in the full system called apply res reductor. It will take in a bool called copy Jacobians. So those are the first derivatives of probably our energy term or our energy function, our cost function. Then we have int min, int max, vec10, reference to stats, and an int tid. We know that from the other reductor, the linearized reductor, for example. And in this method, oh, it's quite simple, I see now. We just have a for loop with int k is equal to min. Then we have k is less than max. Then we have k plus plus. And in this body we simply call active, or we call basically active residuals at index k. So for every residual we call apply res with the argument true. We are not even using the copy Jacobians. We are not using the stats, and we are not using TID, which is a bit weird, but we probably need to leave this signature similar to all the other reductors to keep them compatible with each other. Okay. So this was this very small method, but then we have a larger method which will return a standard vector of type vec(x), which is a vector that can have varying length. And this is called full system get null spaces. And this will take in the different null spaces that we have. For example, standard vector of type vec(x) with a reference to null spaces pose. And we have 3 more null spaces. We have not only pose but also scale. We have FA and FB. All passed by name. Okay, in the function body, what we will do, we'll take those standard vectors and clear them. So same with scale, same with affine A and affine B light parameters. Then we have an integer called n, which is equal to cpars, which is the number of camera parameters, plus frames.size times 8. So for every frame we have 8 parameters. So this is multiplied with each other, and we then add the camera parameters because we assume that they are same for every frame. Okay, next we create a standard vector which contains vec_x objects. We call that null spaces x0 pre. Then we start a for loop with int I is equal to 0, I is less than 6 and I++. Here we create a new vec_x called null space x0 of n, or with n dimensions, and this will change, of course, depending on our current number of frames that we have processed. We want to take this vector and set it to 0. Set 0. Then we want to have another nested loop with auto fr. So we loop over the frames. Here we have for every frame we get the frame hashin, so auto fh is equal to frame hashin. And now we set the null space x0 vector by calling segment. We want to get 6 elements starting from cparse plus fh and then idx times 8. And this segment will be set to the frame hashin null spaces pose.call at index I. Similar with the other segments. Here we have a 3D vector that we extract. We start at cparse plus fh index times 8 again, but we now multiply that value that we have here with a scale factor, which is scale xi trans inverse. And with the last line, we add 3 to that index so that we move away from the translation. And we multiply that value here with scale xi rot inverse. So this is what we do for every frame. And after we have done that, we take the null spaces, or null spaces it is. Oh, this is a bit confusing. This is null space underscore x0, but then we have a null spaces x0 underscore pre dot pushback, where you push back the null space x0. So this will contain these null space underscore x0 vectors. And we also have a null spaces underscore pose dot pushback, which takes in the same null space underscore x0, like this. And this one is passed to this method. Okay, and it seems the rest will be quite similar. So here we have, let me check so that I am not making a mistake. Here we handle null spaces for translation and rotation. Then we will handle null spaces for affine light parameters. And after that, scale. Okay, after that we handle the null spaces for scale, it seems. Whereas they are still quite intertwined, so this might not be exact what I have written here in this comment. But that's at least for the first glimpse that I took, the difference in between the individual parts of this body. Okay, so let's continue by copying this part and then modifying it the way it should be. So first of all, we do not have 6 parameters, but we have 2 parameters. We have A and B. Okay, so this needs to be changed to 2. The rest is the same, null space x0 of n. Then we set that to 0. Then we loop over the frames. We have this frame hashing that we extract. Then we have this null space x0 segment, but here we have 2. We have cpars plus fh index times 8 plus 6, because now we are skipping the ones that we did here. And we have the frame hashing, null spaces, but not pose, but affine with call I, but then dot head to function call. So we take, from the beginning, we take the first 2 elements. And then we update this segment, the 2 elements, in this null space underscore x0. with the other ones, okay, with the other ones we do not need the segment, but we are actually directly accessing this the data, or overriding that with cparse plus fh idx times 8, and then we add plus 6 here, and then we scale it by the A inverse. And similarly, we do it with the B parameter here. So we change that to 7. And this is scale B inverse. Then we have the null spaces x0 pre pushback, null space x0. And then we need to check if I is equal to 0. I like to still add this this block here. If this is true, then we do not need to access the null spaces for the post, but the null spaces for affine A dot pushback null space x0, and if I is equal to 1, then we push back into the null spaces fb with the same value. So there is actually only the possibility that I is either 0 or 1, because if it is 2, it is not less than 2 anymore, and therefore this simply checks, are we handling A or are we handling B? Okay. And with this way, or with this code, we are done with the null spaces for the affine light parameters and can continue with the scale now. For the scale, there is no loop involved. So let me just copy the inner part of this loop and paste it here. So we start with a vec x for null space underscore x0 with n dimensions. We set this vector to 0. Then we have the loop over the frames. Then we extract the frame hashing from the frame. Then we have x0 segment. Then we have 6 again in this case. cparse plus fh index times 8 without the plus 6. And this is equal to fh null spaces underscore scale. Okay, now we need to reintroduce the segments here. So the second segment is 3 and the third one is 3 as well. cparse times 8 is correct, but here we need to add the 3, and we need to scale with xi trans inverse again and xi rot inverse. Then we have null spaces x0 pre pushback null space x, and we need null spaces underscore scale pushback and move it out of this if statement, because we do not have this iteration variable I, so that it looks similar to the pose null space. Okay, and with this we can return null spaces x0 underscore pre. Okay, let's change this null spaces for translation and rotation to null spaces for pose. In parentheses, translation and rotation. Okay, this should be everything with this get null spaces method. I'm thinking about adding the comment for the frame here as well, just for the sake of completeness. So let me add this here as well, and here as well. Okay, and now we are finished with that method. Let's continue with another method, void full system, and then set new frame energy th. Here we want to collect all residuals and make the decision on th. Whatever th is, I think it's threshold, but it's maybe not the threshold, we'll see. First of all, we want to clear all res vec. All res vec dot clear. And then we want to reserve some space. All res vec dot reserve active residuals dot size times 2. Then we create a frame object, auto fr is equal to frames dot back. Then we have auto new frame is equal to fr frame hashion. Then we have a for loop which is an auto and r, and it will loop over the active residuals, and inside this for loop it will check if our state new energy with outlier is greater or equal to 0, and our target dot lock is equal to new frame. So if the target frame is the new frame, in which case it will get the all res vec and push back the residual state new energy with outlier. Like this. And after this for loop, we check if all res vec.size is equal to 0. And if this is the case, then we call new frame energy th is equal to 12 times 12 times pattern num. And then we return. However, this should never happen, but let's make sure. Yeah, this should never happen, but let's make sure that this happens. Okay. Next, we want to create an integer for the nth IDX, for the nth index, which is equal to setting frame energy thn times all res vec.size. Then we assert if nth in IDX is less than cast to int all res vec.size, and we also assert if setting frame energy thn is less than 1 and if this passes, then we call standard nth element and we pass the all res vec, namely the begin, all res vec.begin plus n idx and all res vec.end. Okay, next we get the float for the nth element equal to the square root as a float from all res vec at index nth idx. Okay, and then we set the frame energy th several times. So we have the new frame. From that we have a frame energy th. We set that equal to nth element times setting underscore frame energy th vec median and we set it 4 times in total, where the second one is equal to 26.0f times the setting frame energy th and then const weight plus new frame energy th times 1 minus setting underscore frame energy th const weight. So this is the second one. The third one is then new frame energy th times the same. So the frame energy squared. Like this. And the last one is a multiplication of the old value times the setting frame, no, not frame energy, but overall energy. Overall energy, TH weight times setting, the same basically. Let me copy that. So setting overall energy TH weight squared. So with this, we have set the new frame energy TH. New frame energy TH is set here in those 4 lines of code based on what was calculated before. Okay, now let's go for the last 200 lines of code that we have in the original code. Here we have another void full system, and then we have a method called print opt res. This one will take in a const vec3 reference called res, then a double res l, double res m, double res prior, and a double l exact, and a float a and a float b. We need to create a character buffer, so char buff with 256 elements in total, equal to an empty array. Then we need to call the methods printf as printf. We want to put that into the buffer. And what do we want to put there? A of %f is equal to av %.3f, so a floating point number which we want to clamp or round to 3 decimal places. Then we have num a of %d, %prime d, which is weird. Why is it prime d? I do not know that yet. Plus m of same % prime d, and ab is %f exclamation mark \n for a new line, and then we have the individual arguments for the placeholders. The first one is res at index 0, then square root f cast to float of res at index 0 divided by pattern num times energy functional res in a then we have energy functional res in a energy functional res in M, A, B, and this is it. But of course we also need to log that to the terminal. So log info and string of buff. Now this method is finished. And this will print out some statistics for us. For example, the value of A and B, which I think are our affine light parameters, which should change when we are moving inside an environment that will force the camera to change the camera gain, like the image brightness, and or its contrast. We'll try to keep an eye on that value, because I think the print opt res will be called several times during the Visual Slam is running. So this might be something interesting to look out for. Okay, and now we can continue with the next method, which is the mighty and important void full system mapping loop. So in this Visual Slam we have the different threads, which will contain several loops. One of them is the mapping loop or the mapping thread. We also have the tracking thread and the loop closure thread, I believe. Up until now I have only noticed this mapping loop and not the other ones. So maybe they are written somewhere else in another class. Yeah, but the mapping loop is something that is very central to a Visual Slam system. Okay, here we start with a unique log, a mutex. It's called log, and we'll log the track map sync mutex. And this will be a loop that is running infinitely, maybe not infinitely, but at least it is not stopped directly after the Visual Slam is started, but it will run for some time. So the Boolean variable that will control this while loop is called run mapping, which is a field of the full system, I believe. Here we first wait an unmapped frame. Maybe wait for an unmapped frame rather. Then we have another while loop here, which is controlled using this Boolean variable called unmapped tracked frames dot size is equal to 0. So if we do not have any unmapped tracked frames, then we want to have tracked frame signal dot weight on this lock, and if not run mapping, then we want to break. And the same condition will also be checked after this while loop has finished. Okay, but here we get an unmapped frame. So tackle it. We create a shared pointer of type frame called fr is equal to unmapped tracked frames dot front, and we have auto fh is equal to fr and then frame hashion. So we get the frame hashion, and we say unmapped tracked frames dot pop underscore front. So we take the first unmapped tracked frame, we store the frame hash in here, and we pop it out of this list of this vector, so that in the end it will hopefully be empty, and we will get back into this inner while loop until we get another unmapped tracked frame, and this one continues. Okay, so here we want to guaranteed to make a keyframe for the very first two tracked frames. So if global map num frames is less than or equal to 2, then we unlock. We take this mutex and we unlock it. Take this lock and unlock it. Then we call make keyframe the frame hashion. Then we take the lock and lock it again. And then we have the mapped frame signal dot notify all. And then we continue. Next we check if we have unmapped tracked frames.size greater than 3. Then we want to set the need to catch up mapping. We need to set that equal to true. And we also check if the size is greater than 0, because if there are other frames to track, do that first. So for that we need to lock unlock. We need to make non-keyframe for the frame hashing, and then we need to lock. Next we check an if statement that is related to this catch-up here. Namely, if need to catch up mapping is true and unmapped tracked frames dot size is greater than 0, in this case we want to get the frame from the front of our list. So auto fr is equal to unmapped tracked frames dot front. Then we have a shared pointer that we will create for the frame hashing. Call it fh is equal to fr and then the frame hashing. And we have unmapped tracked frames dot pop underscore front. And then we create a separate scope where we write unique underscore lock a mutex. We call it cr lock of shell pose mutex. And then we call fh set eval pt underscore scaled, which takes in the frame, from that get pose, then frame hashing, frame, and fg2l. And this is it for the if unmapped tracked frame size is greater than 0. But we have an else part. So else if the setting for real-time max kf or need new kf after is greater or equal to int of frames.back id. Then we want to unlock the lock unlock, make keyframe, pass the frame hashing, and we need to set need to catch up mapping is equal to false, and we need to lock the lock again. Else we want to unlock again and call make non-keyframe for the frame hashing, and then lock. Okay, this is the else block, and after that we want to call mapped frame signal dot notify underscore all. And after that is done, so when this while loop exits, because we want to we do not want to run the mapping anymore. For example, when we are done with processing the image sequence, then we want to log an info in capital letters, mapping finished, exclamation mark, of course. Without an end line, which I do not like, so I will end the line here by myself. Alright, this is the mapping loop here. That's everything with this mapping loop, but we still have about 130 lines of code to go. So we are not finished with the full system yet. So let's continue with a method called FullSystem save all. This one will take a constant string reference to a file name, and as the name already suggests, it will save something. What will it save? It will save all of the keyframes. So we will create an offstream object called fout, file out, and this one will get past the file name and also iOS out or iOS binary. So we'll create a file that we'll write here. This will be a file that will be created if necessary, and will be a binary file. We can check if this file or the output file stream object is not created properly, then we can return false. Otherwise, we create an integer for the kf for the number of keyframes, which we can get using global map and then getting num frames. Then we call fout.write cast as character pointer and nkf and size of int. Then we can also get all keyframes as objects. So not the number, but the actual keyframes. All kfs is equal to global map, and then get all kfs. Then we create a for loop. We loop through auto and frame in all kfs and we will now call frame save with the fout object. Then we will close the output file stream, and we can then log an info with done. I will change this to something more helpful. Maybe like writing X keyframes to file, and then done. Then we have NKF, like this. I hope this will not introduce an error, because I will have a typo, but it seems to work out, I believe. Okay, I could also print out the file name. Yeah, let's do that. Why not? It's not that we have to finish a FullSystem.cc file. We have enough time, right? No, I will keep it short. So this is the file name. And that's it. Okay, this should be fine. We need to still return true here. Okay, now if we are writing keyframes to a file, we of course need to be able to load them. So let me copy that method, because it's quite small. And let's rename that to load all, the constant string file name, and then we have not an OF but an IF stream called fin. This will get the file name, and that's everything. Then if not fin, then we return false. Then we have int numkf is equal to 0. Then we have fin dot read a character, and we have this numkf here, size of numkf. Okay, now we need to store the keyframes somewhere. And we will store them in, what do you think? A vector. A vector of type shared, pointer, frame. This will be called all kf as before. But we need to resize this vector all kf resize by the numkf and pass the null pointer. Okay, after we have resized them, we want to initialize this frame object here in this vector. So every single frame object we want to initialize them. And I have this loop here already prepared. So I will just keep that and rename it with a reference to kf in all keyframes. And then kf is equal to shared pointer of type frame and initialized with new frame. Then we have int I is equal to 0. And now we are reading the file. So we have a while loop. If not, fin dot end of file. And I is less than integer of all kfs dot size. So while we are actually reading, and we are reading objects or elements that are less than the total size that we have already read in here, then we will create a shared pointer of type frame and new frame. And set it to all kfs at position I. So we take the reference to our already existing list of keyframes. And then we say new frame load from the input file and put it in the new frame, and the total number or the list basically is all kfs. And then we increment I so that we can make sure that if we are reading more than we are actually storing, things will go well still. After that, we can close the input file. But what is different to writing is that now we need to show the keyframes that we have loaded in the viewer. So we need to check if we have a viewer. Then we want to call the viewer and then publish keyframes all kfs false hcalib and then mpch. Then we have to set the frames object, because now we have read in the keyframes from the file. So we need to update the internal data structure that holds all the frames. And this is the frames object. And we set it to all kfs. And furthermore, we also need to loop through all the keyframes. We make a reference to the keyframe, loop over all kfs, and then we have the global map, and add the keyframe to that global map so that it can be optimized. Okay, now we log an info where we say that we have loaded total and then frames.size keyframes, and I will keep that here from file name, and I will also keep that done. Return true is fine. Let's check the file name if this is the same. Yes, it is. Okay. So this is this file. The last approximately 100 lines of code that are left. So now we need to implement the printing of results. And there are various methods. So there's there are different ways how we want to print the results, and therefore we might need to implement different ways to do that. For example, one of them is void full system and then print result, which takes in a const string reference to a file name and a bool print optimized. Okay, so here we want to have a unique log mutex called log track mutex unique log mutex log track mutex, like this. And we have another unique log mutex called cr log, which is the shell pose mutex. And we will create a standard OF stream called myFile with a file name that was passed. And next we need to set the proper precision, because we are probably printing numerical values that have a lot of decimal places. So this needs to be set here using myFile and then standard set precision to 15 decimal places. Or it's even not only related to decimal places, I think it's also related to very large numbers. Okay, next we need to get all the keyframes. So auto all KFS is equal to global map, and then get all KFS. Then we need to log an info, or we can log an info with total keyframes being all KFS dot size and then end line. Okay, next we will have a loop with auto and fr. We loop over all KFS. Then we have to store the transformation for the world to camera. So we have an SE3 and we call it TWC, transformation from world to camera. And we also have a sim3 that includes scale besides rotation and translation with SWC, which is probably only the scale that we are interested here, but we will see. Next we will check if we want to print the optimized. And if this is true, then we want to set SWC equal to FR and then get pose opti dot inverse and TWC is equal to SE3 of SWC dot rotation matrix and SWC dot translation, which is a nice way to write that. And this is, I think, the Sophos library that is responsible for that, because Sim3 is in the Sophos library. Next we have the else part, where we only take the TWC and set it to fr get pose dot inverse. So I'm not sure what the difference is between the get pose opti and get pose. Probably the one is optimized and the other one not, of course. But what is actually happening when we are not using the optimized pose? Is it like the initial value, or what is this get pose returning? Okay, so now that we have checked what kind of pose we want to print, we take the poses and we write it to the myFile object using this this operator, the bit shift operator, with fr and then timestamp, and then we simply add a space and print out twc dot translation dot, oh, this is a function, dot transpose, and this way we continue. So we print the translation, and then we print SO3 and then unit quaternion, and then dot x. So we now take the individual components of the rotation quaternion. So we are not printing the SO3 matrix, but we are printing or writing the quaternion into to the file with the order X, Y, Z, and then W. Okay, and we cannot forget to add a new line, because otherwise this will be a very chaotic file. Okay, now we can take the myFile.close. Take the myFile and close it. Okay, so this is the one of the methods that can be used to print the result to a file, to this file name. And now we can copy that. I believe, I hope that we can copy it, because now there's a different version which is called similar print result, but now we add kitty to it. Okay, print result kitty. This has the same signature. Print optimized is here as well. But now we have a log in the beginning. we log saving kitty trajectory dot dot dot, and not to forget the end line. The rest is similar. We have log and cr log for track mutex and shell pose mutex. Then we have an off-stream object, but this time is not called my file but only f. We do not have the set precision here, it seems. So let's, well, I would like to keep it actually. Maybe let's add it as a to-do. My own wish to have this here. Then we get all the keyframes from the global map. Okay, this is not necessary. We will have a for loop that loops over all the keyframes. Okay, the rest is a bit chaotic to me. I actually do not like the way it is written in the original code base. I like it more like this. Okay, so we definitely need I see what the problem is now. But well, we definitely need a TWC. Okay, but there's a capital letter T WC and a small letter TWC. Okay, but yeah. Let's still do it like this. So we have so the small one is a vec3. This is a translation vector. This is a transformation matrix. And we have this SWC, which is a similarity transformation matrix. And the new aspect here is that we have a rotation matrix as well. A mat33 called RWC. Which is a rotation matrix. Okay, now depending on what we want to do, if we want to print the optimized value, I'm sorry that I'm a bit slow here. I really need to think about why they did it that complicated way. Okay, so if print optimized is false, that's even the thing that they begin with. The print optimized is false case, so I need to think even more. So if this is false, then we want to set TWC as fr getPost.inverse. That's fine. But then we have RWC set as TWC dot rotation matrix. And interestingly, not the inverse, because TWC is the inverse already. Okay. And then we have TWC in small letters being capital TWC dot translation. Okay, so far so good. Now we do not have my file, but we have file. And it doesn't even matter if it's optimized or not. This printing of this file is always the same. So now we have that. And with the optimized being true, we set SWC to fr get post opti.inverse. This is fine. Then we have RWC, which is equal to SWC dot rotation matrix. And we have the small TWC being SWC dot translation, I believe. Yes. Should be like that. I hope I did not do any mistake. Yeah, I believe this is correct so far, and then we need to change this one, which now does not contain fr timestamp, but fr ID. And here we will have this set precision. So I will comment this in again, but the difference is that now the precision is set to 9, which might be important for the Kitty dataset, or the Kitty evaluation tools rather. But this shouldn't make a big difference. Okay, so we print the frame ID. Then we print a space. Okay, let me move this space here. Okay, now it is written as follows. we have the rotation matrix RWC at position 0, 0. And then we have a space, and then it continues. So we have rotation matrix 0, 1, 0, 2, and then we have translation vector TWC, small TWC at 0, and then we have a space, and then this continues. So this is only the, it's not the full 4x4 matrix, it's only the 3x4 matrix part, which is sufficient, as the last row is containing 0, 0, 0, 1 anyway. So this will be 1, this will be 2. And this is 1, this is 2 as well. And this is 1, this is 2. And this is 1 and this is 2. And here we will add an end line. And this is it. Then the file needs to be closed. So I have optimized this code a little bit compared to the original code base. In the original code, this is being written twice. So this is like a duplicated code. And I have written it this way so that I first calculate the values that I need and then print it, because this will not change. Only the values change here. Alright, so we close the file and then we can print last log info called done. And an end line. And we finish off this print result kitty method. And fortunately and happily, we can finish the whole LDSO space, namespace, and this way, if you really watched the whole video series up until this point, up until this part 10, congratulations that you really have like this stamina. I already began to struggle, to be honest. So writing this whole piece of code was, yeah, it was not very funny, but it was a little bit funny at least at some places. I have to say that some things made me smile and a little bit happy. So with this, I think I will call it a day or a night, and I will still give you a short overview what we will do the next time. So now that we have written the full system, the FullSystem.cc and the FullSystem header file, unfortunately the next step is to comment out everything and try to see what we can use. So if we take a look at the FullSystem.header file, we have this image and exposure, but we do not have all of the other things. And what we will do in the beginning is we will take a look at the constructor and the destructor, The constructor, it seems, only takes in the op vocabulary, which we have due to the data types that we have implemented. Here the num types. But still, if we look at the implementation of this constructor, you will see that it will initialize the course distance map, the course tracker, the course initializer, the energy functional, the camera, and the map. And this is those things, we do not have those things yet. So for the constructor to work, would need to go ahead and implement everything. Yeah, and this is a little bit of, yeah, this is not nice to know. So yeah, I will need to find a way to at least quickly get that to run. I think the camera and the map is not very big of a file, but the course tracker and the course initializer, I think they are quite extensive. Okay, but this is something for the next parts. And knowing this, I thank you very much for watching. I hope you enjoyed it a little bit. And I will see you next time. Goodbye. See you in the next part.